Okay, let's get started. Today, the lecture only has one word as a title, and the word is equilibrium. Equilibrium is I think everybody thinks they know what it is, but it's not clear that you know what it is. It's one of the things that for me has always been quite a difficult subject. In economics, I took this picture out of economic equilibrium in Wikipedia, and they illustrate it like this. They have the usual demand line or supply line, and their idea is that suppose you supply this, or you demand that, then you're not in equilibrium, there's some kind of excess, and then you would drop the price. Everybody would, this guy would increase his demand, this guy would decrease the supply, until they reach equilibrium here. Right? This is just a primitive idea of economic equilibrium. Now, what I want to do with this lecture is show you how that corresponds to the mechanical or physical idea of equilibrium. Now, what is equilibrium? There's a problem because it's not so clear what equilibrium is in mechanics. Kunja, would you be able to tell me what equilibrium is?
Two kind of forces meet each other.
Okay, so he says that the sum of the forces are constant, right? Huh?
Yes.
They meet each other. So this sum, they're constant. Okay? So this is actually not equilibrium, because if the net force is zero, a body can go at a constant speed. So this is what we call rest, or a steady state. Things are just moving along. You can still bring this system to equilibrium by breaking it down, and then it will move, right? So the problem is Newton doesn't tell us what equilibrium is. He tells us what rest is. This is also called the steady state, or a stationary state. So the problem seems to be that you can have a constant, velocity not in equilibrium. So what would be equilibrium? Well, that will be when not only the price is in equilibrium, but also velocity will be zero, right? Yeah. Right, so the idea is quite simple. You have a mass that's going at a finite velocity. There is your reference frame. You can crash it against the wall, and you can get some energy out of it, and then it will be in equilibrium, right? So if it's not Newton's laws, then what is the governing principle of equilibrium in mechanics? What law tells you whether you have equilibrium or not? Or whether you're going towards equilibrium. Does anybody know that? Does anybody know that here on the silver screen? So it's not a balance of forces.
It's the energy.
Energy?
Yeah.
What do you mean energy? That's not a law. Conservation of energy, you say.
When energy is going to zero.
Energy is going to zero.
Yeah.
Okay, so you say, here's an idea. So the total energy in the system, the change of that, right, is negative, right? And then when the energy is zero, then you have equilibrium. That's what you're trying to say, right?
Yeah, but it's, yeah.
So what's wrong with that statement?
Still potential energy.
Yeah, and there's a law of conservation of energy. So how in the universe, if you have a big system and it's isolated, how would it go to equilibrium? Suppose I take some system, there's all kinds of stuff going on, and I'm not putting energy in it or out of it, right? How would it go? It can still go to equilibrium, right?
Can you then maybe only talk about a dynamic equilibrium?
No, you can talk about equilibrium. You can take an isolated system and it will go to equilibrium, right? We know that. So what is the law? So it cannot be energy because energy is conserved. So really energy, because you're on the right track, okay? But you're almost there. You need another law. You can't have a law just about energy. So if things are in equilibrium, suppose they're in equilibrium, so I have this thing, it's over here. Will it go out of equilibrium? No. What if it's out of equilibrium? The marble is over there. Would it go to an equilibrium? Certainly. It will go like this, whoop, 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 and ultimately it will just settle down, right? This is an isolated system, right?
Minimize the energy or the potential energy? Or just
In this case, it will tend to minimize the potential energy. But why? Energy is conserved. What's happening to that potential energy?
So in this case, it's being dissipated.
It's being dissipated. What does that mean? That's right. So energy is being dissipated. Huh? So let's call the rate of the dissipation S. And then if it's being dissipated, then this is bigger than zero. Then it's being dissipated, right? Huh? What is this quantity that tells you? But why should this be zero? Why can't this be negative or something, right? Or zero, or you know. So you're requiring that energy can only dissipate, it can't congregate, right? Huh? So you need a law to tell you that. What law is this?
The second law.
This is the second law.
Has
What?
a question. Has something to do with entropy? In the
That's
storage?
right. Right. That's right. It has got something to do with entropy, but that's just saying something, or that's replacing it with another word that you don't know what it means, right? Huh? So you kind of think you know what you mean because you've heard it, but now, if I say, how does that correspond to equilibrium economics, you have to kind of come up with what entropy is, right? So you are right, Pete, huh? But I want to tell you, so what's going on here? So slowly we're getting there. So the energy is conserved, however, the entropy is not conserved. It can just keep increasing, right? So
I think
the
like in a more general sense, you can also explain this using a Lyapunov function, right? So if you can, like for general dynamic systems, if you can find a Lyapunov function that has like a local minimum at a certain point as positive definite, then you will achieve stable equilibrium. And in this case, you can use the energy as like Lyapunov function, so that would like then result in being stable equilibrium.
That's right. So what you want to say is that, see what the old timers said, they did what Chit suggested. So they said, okay, we got this box here, I got all this particle, all this kinetic energy in there, right? Huh? Okay, it's going every which way, right? Or I take my hand and I start rubbing this table, right? So I have a certain amount of kinetic energy. But now I look at the table plus my hand as a single system, then after I do the experiment, I do the rubbing, right? Huh? Then all this kinetic energy is gone, right? Now where did it go to?
Heat.
Heat, yeah. So, that's cute. But what is this heat? It is energy, but it's energy that's dissipated. How did it get dissipated? There's one way to say dissipated, another to explain to me what happened when I started rubbing this.
The molecules start moving.
The molecules start moving. So the kinetic energy of my hand, right, went into the molecules. You know, the friction, it just knocks over a little piece of the table, a little molecule, and that one starts moving this way, and that one starts moving that way. And all these molecules are moving faster here, all right? Okay? Now you can say, well, you know, so if you take the derivative of this thing, then this is zero, right? And then you can see that this thing must be smaller than zero if
Unit-wise, you're missing an S, right? Because T is temperature and Q is heat, I'm assuming.
yeah.
So the units don't match up right now.
No, this is heat, so this is in
In joules, right?
yeah, this is also in joules, right? Huh? Right?
But you, T is in Kelvin, right?
No,
or,
it's
or is that a kinetic
kinetic energy, sorry.
Oh,
Okay?
okay.
Sorry.
Yeah.
We're not doing thermodynamics, we're just doing mechanics here, right?
I know because we're also talking about entropy, so I was
I know.
a little sure.
Our chemical engineer here is not following standard mechanics terminology. So what Emil says, I'm going to watch this thing. I want to see this decrease. That's also the Gibbs free energy that you can see decrease. Okay, because this energy is available to do work. You can knock my hand against some kind of mechanism and it will start moving. But the movement of the molecules is not available to do work. You know now, it's going every which way, and you have to make a panel that's so small, it's the size of a molecule, it won't work. All right? So it's too small. You can't figure out where it all went. That's what we mean by dissipate, right? So this thing is bigger than zero, right? So what is heat? Heat is just all the kinetic energy that was lost from your hand and went into all these other things, right? So when you feel something, you feel it's hot, you feel all these molecules hitting your hand, and the average impact of that is what the sensation of temperature that you get, all right? Now this kinetic energy, you can write a small change as we know that, right? And a small change in heat, I'm just using a D now because I'm there. You can write it also as a sort of the price to pay, which is the temperature. And this is now confusing, right?
Maybe use a tau for that.
Yeah. This is the temperature. And this is the entropy. Yeah? You can write it like this. All right, and then we're back to what Pete says. Like, has this got something to do with entropy? Yes. We define some kind of stock variable, right? Some kind of extensive property, you would say, because thermodynamics. In the same way, you define price here, you know, that you can match up with some kind of flow, which is this thing, this tau, okay? That's the temperature, and then you get the total amount of heat that you dissipated, all right? That's the mechanism. So the second law of thermodynamics, you can say it's the law of increase of entropy, but that's really not so great because, you don't know what is entropy, right? You can better say it's the existence of equilibrium. Right? So because you have a quantity that you know will only increase, all right, you know that this equation, if you set it equal to zero, you know, the changes, that at a certain point, there will be no more, you know, this is going to reduce the kinetic energy until it's zero, and then the term is over, and it's at equilibrium, right? Now the kinetic energy is half p squared over m, and when that is zero, then it follows that p is zero, right? And hence the velocity is zero. Okay? So, equilibrium is all about the second law, about the generation of entropy. What is the generation of entropy? That's just a measure that we use to say how dispersed the energy is. It just went in all these degrees of freedom. Now, suppose I was just waving it through the air or the vacuum in my head. Is there any entropy generated? No, because I'm not hitting anything. I'm not doing any transactions, you know. So I just, you know, well, yes, I am, because I'm like probably having all kinds of friction in my hand. But in principle, if a comet is going through the sky, there's no entropy being generated, right? But as soon as it starts hitting air molecules and it comes in the Earth's atmosphere, then it hits all kinds of little things, and those things go every which way, all right? And then you have extra degrees of freedom, and in those degrees of freedom, then you allow yourself to generate entropy, all right? Okay? But if this comet hits, is a billion ball, and it hits another billion ball, and that just takes off, now with that momentum, then, and it's an elastic collision, and that's just the definition that there's no entropy generated, then we know where everything goes and there's no entropy. All right, so nothing is dissipated. Now, I can hit 2 billion balls, and you would say, in a sense, it's dissipated, but if I'm keeping track of where those billion balls are going, then we won't say it's dissipated, okay? You follow that? So the word dissipated has to be taken in a very precise sense, that we're losing track. We only know what the average motion is of these other billion balls that I hit, okay? If you keep track of everything, then, there's no entropy generation. Now, so it is in economics, okay? So this whole story, now, you see, now we reap the rewards of having done all this mechanics. So we can just think of a billion ball or a particle like an agent, right? There's just an economic agent, and there's a big guy come around, and he's doing a transaction with multiple small ones, and they're all going every which way doing stuff with it, okay? And we're not keeping track, so we have this whole system, a whole economy, and somebody in the central bank like does something ginormous, and everybody in that economy is jumping left and right, then you've dissipated the income, right? The surplus. Kinetic energy is the surplus. You've dissipated it, you've lost it, right? It's still there, but it's in the system, and there's no way you can get it out anymore. What does that mean? There's no way you can go between two people and set up a little trading operation to get this tiny amount of surplus out of there. It won't just cost you too much money. Huh? All right? Even if you're able to determine what the reservation price is, what they have, or what their stock levels are. And this is also in quantum mechanics. At a certain point, the particles are small, so small that you can't determine anymore what the momentum and the position is. All right? Because you're going to hit it with a photon. It's got some type of energy in there, and a thing, before you measure the momentum, you messed up the position. Now, so it is in economics. In order to find out what the reservation price of somebody, you got to kind of do something economists would call a tautology, a little transaction, like your credit card does that, like 1 cent or something, huh? Okay? But if it's small enough, the stuff you're looking at, then you won't know anymore the stock because you bought something for that little test fund, okay? So if in the Netherlands we use 5 cents as the minimum, currency, then if you buy something for 5 cents just to check, you won't know what the real price was or the real amount that you bought. You just know that the product of the two is, okay? So there was always this thing like, okay, why does entropy exist? Because in principle, if you have Newton's laws, you can follow everything. So there shouldn't be any dissipation. We shouldn't have any entropy or heat in this universe. But what they found out with quantum mechanics is there's no way of measuring momentum and position for small enough particles. So therefore, there is no way you wouldn't be, you will always get entropy generation. Let alone that if you have a gas here with a mole, which is 10 to the 24 little gas molecules, there's no way you can calculate this anyway, right? Even if you had all the computer power of the world. All right? So, equilibrium is all about the dissipation of the surplus, okay? And that's what we're going to talk about today. Now, last lecture we talked about the convenience yield and the analog, the potential energy, which are the benefits, all right? But this will not cause equilibrium. Yes?
Look on the right side of the board.
Look at the what? Oh, yeah.
There it is.
All right. That took us 25 minutes, but we found it.
I saw the video and I didn't want to.
What does a spring do? Well, you know what a spring does. You have this thing here, And then, you know, suppose you pull it out, suppose here's the equilibrium position, what would be the equilibrium position when the spring is not applying any force. The thing is not gonna, it's gonna go back, it's gonna try to go towards equilibrium, but it will like overshoot at this point, right? So if you look at this with a spring and a mass, the thing will do this, right? And this guy will do that, right? And there'll be no dissipation because you'll know where all your surplus went. Either the surplus is being stored, potentially, or it's being, you know, it's operational surplus. It's actually being transacted. So you know where everything is. So the thing is, it's going up and down. It will never reach equilibrium. And indeed, we plotted the phase trajectory. Here was the price, and here was the scarcity. And it was just like circling forever around the equilibrium point, which is here, right? Because only here is both the kinetic and the potential energy equal to zero. So only here is the total surplus of the system zero, right? So if Emil says you have a Lyapunov function, one thing you can do, if you plot this in time, that you see that the amount of surplus is shrinking, all right? Or at least not increasing. All right? So springs and I elements are C elements, so masses of springs, they don't generate entropy. They store energy, right? Demand and the convenience yield storage, you know, physical storage does not dissipate the money, does not cause economic equilibrium. It just causes a trade cycle with the thing always going up and down, right? So we need another element. We need an element that causes equilibrium to occur. And that element is the discussion of today, all right? So what I've done with this one slide is tell you that the concept of economic equilibrium or engineering or physical, mechanical, say, it's probably more thermodynamic, these are the same. And we're going to have a notion of entropy in economics, but it's not, you see, there's lots of books written about entropy in economics, okay? And because they know there must be something, right? And what I don't like about it, they never really say what it is, they just call it entropy, right? And of course they can't really because they don't have any kinetic energy. They don't have an I element, you know? So they can only do this kind of hand-wavy stuff, you know? A little bit the classical thermodynamics, you know? What we're going to do is make the connection, it's called, sometimes called kinetic theory, right? So that you look at entropy from a molecular level and try to explain how the phenomenon occurs, all right? But I did get a good suggestion of Emil. I have not thought of that, is that in engineering, we don't usually use entropy. We use more these Lyapunov functions and Lyapunov coefficients that squeeze the energy. So I should really look into that, or somebody else can write a thesis about it. All right? Huh? That's probably more what I'm going to do. So. But anyway, the take-home message here is you should make a distinction between rest and equilibrium, right? Equilibrium, you know, now there's no more generation of entropy, so no more dissipation of the surplus. But you also know, because of the second law, that this is always, okay? We're just going to assume that. Now, we're going to be talking about, so now we have these I elements, these C elements, now we're going to bring in these dampers, these R elements, right? So they're the ones who are going to generate the entropy. Now, why do they do that, right? Let me just like paint the picture of one. Here is a dashboard, it's called a dashboard, right? So there's like some oil here, these are little oil particles, right? This is some plunger. And then what they do, they make this little aperture here, little hole, and then if you push on it, then the oil will have to go through here, and it comes spurting out on the other side, going every which way, right? So what's going to happen is that as you move this, so you take, say, a mass with some kinetic energy, the kinetic energy of this plunger thing, or this mass, will all get dissipated into the little molecules, right? Oil molecules. That's what happens, right? So the temperature of this thing will rise. You will see that, it will get hot, right? And the entropy is going to increase, right? Until the limit, you know, now, when the velocity goes to 0, then entropy increase will be 0, all right? Because you're not hitting any more molecules, you're not dissipating any more substance, all right? So, the economic picture of this damper is like, here's one big agent, right? And here are all these little agents, and you just got a ton of money that you sold, you know, maybe you did a collision with somebody else and you sold the house, you got all this money, and now you're buying a little ice cream cone from some ice cream vendor, and you bought a loaf of bread somewhere, and you bought this, you know, now you went to all these other agents with all these degrees of freedom you haven't modeled, right? And that's what you spend your money on. So one way I like to think of this is, if you have this damper, I don't know why I do, now this is some dimension Q, but here, economically, are all these other goods, you know? So this is Q 1 through Qn, and this will be your, like the good you're looking at, right? But you're not gonna look at these, you know, these are ice creams and this and pencils and all kinds of stuff. So you kind of group all of these together with some sort of average energy that's in there, average surplus, all right? And that's what you're gonna call heat, or probably welfare, all right? So that's the picture you should have in your mind when you see a damper, all right? Yes?
I think another way to look at a damper is as some sort of broker. So on the left side you have the velocity of the demander, and on the right side of the supplier.
Right.
And then the broker, he takes the difference between those quantities,
Right.
he takes out the energy and matches them up.
That's what I want to do in the next slides. But if the broker, you see, yeah, but I really like the idea, but you have to say something more, because you can also take out the kinetic energy here with letting put a little motor in here, you know?
Yeah.
You know? And then, you know, you just take out this, and you're also brokering, you know, the force, right, economic force, but you're actually taking the surplus out.
Yeah, you
Right?
do something with it.
Yeah, you start doing something with it, you know? So you can like take a dynamo, right, or a generator, and then you get electrical energy, and you've turned your kinetic energy, which is like rotating your generator, you know? And you can also think of that as a broker, except he's using his profits now in some productive way. This damper is a little bit more. He is a broker, but at the same time, he's just wasting all the money by buying pencils. You know, there's a lot of like little expenses and all kinds of goods.
Yeah.
Right? Huh? Now, I want to do this, this whole business in 2 steps. So I did explain why using the surplus and energy principle. But now I'm going to like jump that idea, and I'm going to go just to signals and say what happens. And then that's the same way we did I elements and C elements, you see? And then later, when we know what happens, what the laws are, the constitutive relationships, we can then calculate what the energy is going to be, and then we'll find out how much we're dissipating, all right? So I'm doing it a little bit. I first wanted to say what is energy, where we're going to end up, the energy thing, and then start going from the signal, you see? So, kind of came out like, oh, that's what I want to do, but that's not how I wanted it to come out. It's, I'm happy with the question because Here I just say what equilibrium is, where we're going to. I can only do that using the notion of energy or surplus. But now I'm going to junk it, and I'm just going to do signal-based stuff. F is F times A, or F is B times B. All right? And then later on, calculate what implications this has for the surplus. Now, is the pointer is not here. Huh? So, there's some confusion here. So I'm going to first talk about what this damping is. Part of this I already did, right? So how are we going to connect these demand and supply line and this movement to equilibrium with our picture of what's going on here mechanically, right? So what do I see here? I see supply line. So here, I'll just put a mass here with supply velocity, positive, right? Huh? Then I see demand line. All right, so I put that one over there. And then I see some point of zero here, all right? This is what they chose, right? I don't know. Huh? So I'll put this thing here, mark it.
I think you mixed up demand and supply.
Supply is positive, right? So, huh?
Yeah, but it says MD.
Oh God. Yes. I did. Actually, I should have just left it out because they're the same mass, because they're the same slope. All right? So, yeah, thank you. Huh? So, blue is supply, huh? Indicated by D here. And red is demand, indicated by S. All right? Exactly. So, this is the first thing that a lot of students get wrong, is that when you look at a picture like this and you think I got one mass, no, you got three, right? You got one for the blue, one for the red, and one is the inertial reference frame. Now, a lot of things that go wrong is that people say, well, this can't happen because supply always has to be equal to demand, and well, what's going on here? Here I can have a situation where this one is over here, that one is, I don't know, could be over here, right? And this one is over here, or over here, right? So you see this whole graph makes no sense from an engineering perspective, right? And there's nothing preventing that. You're just not doing any interactions, or you're not trading, you're just cruising along. You're just breathing air or drinking water. You don't really care about anything, all right? So don't think, that it only makes sense to draw pictures like this when the thing is in equilibrium, right? And also, you don't have to have a situation like this either, that there is some future where they're going to trade. No, they can just do whatever they do, right? There's a bit of a leap, because in reality, of course, it never happens, But you should realize that in reality, you never have Newtonian rest either. There's no particle that goes at a constant speed when you leave it alone. Everything comes to a rest with respect to the inertial reference frame.
So if there's no trading, what does the velocity represent?
That's just your quantity demanded. Who cares where it came from, right? Right? This is what it is.
The quantity that you would like to have, not the quantity that you're getting.
You can also think of it as the thing you actually get it. Yeah, you're getting, right? Yeah, but who are you getting it from? You don't care.
Yeah.
You don't worry about those things. Only later, when there is scarcity or frictions and those, do you get forces associated with getting it. But what you have to imagine is that when there are no forces, you just have this graph, and you're here, and this is your price level with respect to the market, and this is your quantity supply, and this is what you're doing, right? Who cares what it goes to, where it comes from? This is what economists do, right? Now, if you have a particle hurtling through space, who cares where it goes to? I mean, of course, space can't be infinite and all this, and it must be attracted by something, but maybe not. I mean, if you imagine all this away, then there are no forces acting on you, you got infinite space. And that's what you got to do here. You just imagine everything away. Then this thing is just going to go on. Where did the goods come from? I don't care. Space has no zeros, and there's no scarcity, there's no this. Do I have economics? Oh, not really, right? I have prices, but no price changes. So, do I really have mechanics? Well, not really, right? So a bunch of masses going across the speed. Okay? Right? But it's an abstraction you got to do before you can start thinking. Don't build in equilibrium yet. You don't even have the second law. You don't have anything generating entropy, right? This is a mistake students make, right? They build everything in, and then they say, well, it has to be the real market. I mean, otherwise it won't work. But that's the same as saying to Newton, well, look, it has to be real particles on Earth. Otherwise, this your first law is just is bogus. You know, you could say that, but you're going to be on the losing side of history. It's just not the right thing to do, right? It's better to think all this away and just focus on the single issue at hand. All we have is two types of demand or supply, all right? And then unhindered by anything. Just keep that, your mind clear, you know? Right? There's no storage. Okay, so no springs. And there's no transactions because they're not linked. So no brokers, no nothing, right? So they say, we'll just keep going. You say, well, how long can it keep going? Well, I never defined zero and I never defined the distance, right? So cannot be answered. Clear? Because I remember you getting stuck on this. That's why I'm kind of happy with your question. And I see many students get stuck on this issue. Okay? And you can say, well, this is not what economists do. That's right. You know, I've heard that argument, but we don't care. You know, we got to take economics and place it into the concept of mechanics. Otherwise, we can't do anything. All right? That's the game here. So even if you don't like it, do it anyway, right?
But then in this picture, if you were to have the mass as difference, so for supply and demand, would that in the graph on the right be two different slopes for the graph?
Yeah, sure. All right, but this whole graph makes no sense because this one goes to zero here, not at p is zero. This one that does go here at p is zero. This one has to be shifted down. This one has to be flipped around. And then who in mechanics ever drew, you know, an intersection of two lines to find out what equilibrium is? You can't do that. So all these graphs, they're just suggestive of a process that is governed by forces, not by prices. There are no forces really here, right? So get away from the idea that you got to model it in this way with an intersection. It's just not the way it works, you know. I'm going to try to get as close as I can, you know, but in general, it's not the way it works. You know, it's like saying, okay, I'm only going to have I elements, and then they behave in such a way that there'll be some equilibrium. No, you got to introduce other elements. You got to introduce force fields. You got to do this. You got to do that, right? Okay. So when you see pictures like this, you gotta see that basically you're gonna have, you know, two lines, right? Like that. But this one probably has to be flipped one way like this, one way like that, shifted down. You can forget how you do it, right? And then you lose all the idea of this intersection point. You know, but you could say that if I'm standing here and I'm looking at this system, all right, then it will be going with some kind of central mass, right? There's a central mass motion depending on whether these things are connected or not, right? Now that thing I could imagine is this thing, right? So maybe this point is what they mean by the central mass motion. Now we'll just assume that, you know, but for the rest, I don't know. They run this axis this way and this axis that way. So where did this one start at zero to run that way? I mean, you can take it the way you want, right? So the way I would interpret this will be the center of mass motion, all right, and the momentum that belongs to that, okay? And you can do anything you like, all right? Okay? Clear? I need the questions, right? Because these are things that are so obvious from a mechanical point of view, but when you translate it to this, you get yourself so confused, you know? I see it time and time again. Now, how is this system going to get in equilibrium? Well, you need these, if this is the center of mass motion, we need some interaction between these things so that they go together at the center of mass motion, right? Okay? How can we do that? Suppose I put a spring in between these. Is that going to work? No, not really, because it's going to go, huh? So it's not going to keep one velocity. Huh?
Yeah, but then you have marginally stable. So it's still some kind of equilibrium.
So yeah, but this is also some sort of equilibrium. It's a rest, right? It's not equilibrium in the sense of entropy is maximal, right? Okay, it's some kind of rest state. It's like
it's
pendulum going up and down.
Equilibrium.
So what?
It's Lyapunov stable equilibrium.
Equilibrium, right?
So the energy doesn't increase, but it also doesn't decrease.
Decrease. Yeah. Okay. Huh?
But at least it doesn't increase.
Yeah, so sometimes they say you're on the center manifold, so you're always moving around the equilibrium state. So if they do these, they have this course, right? I don't know what it is.
Non-linear system.
Non-linear system. So what they do is they look at the phase plate, right? Yeah? And they call this the equilibrium state, right? So that's correct. This is what I would call the equilibrium state too. So there is no more surplus, right? Okay, so everything is going at the same speed as the reference frame, right? And in addition, right? Yes.
So
What?
in that position as well.
Yes, right, exactly. That is equilibrium. Then you have the center manifold, that way you can like buzz around it, right? Or you can do something like this, that you converge to that, or you can do all kinds of crap, right? But they're technically not pure equilibrium states. Okay, they are states of rest or steady states, sometimes they're called, right? Or stationary states is an even better word, huh? Okay, but the word equilibrium gets thrown around a lot, huh? The thermodynamic equilibrium only happens right here. And even then, it's a relative concept, right? Only for the observer standing here. So over there, he might see like, hey, I can do something with this. Right? It's always relative to the observer. That is what entropy is, right? Yeah, exactly. So a spring is not going to work. Well, we know that a damper would work, right? Huh? Right, so go, and the limit, this thing will just go at a constant speed, right? You look unconvinced, Chet.
The spring is always in combination with a damper.
No. You can put a damper between two.
Yeah, sure.
What?
Okay.
Yeah. Yeah, why not?
Well, in cars they use them in a combination, but I was.
Sure, but
You could only do shock.
yeah, what about this doorstop here?
Yeah, sure.
There's no spring in there. Well, there is.
But it's tuned to appear not to be.
But okay, you have a shock damper you're thinking of in the car,
Yeah.
right? Take out the spring. Why wouldn't it work? I mean, sure.
Come back to me later and I will.
Yeah.
Yeah.
No, I mean, look, there's no reason why not, right?
I think it would be uncomfortable.
Yeah, so you just go
Yeah.
down and then you get and you go up a bit and then you go down.
Yeah.
So it only dampens out the force on the mass.
The damper stops velocities, right? And
Works both ways. So if you give it a velocity, then it gives you a force, and if you give it a force, it gives you a velocity.
But suppose I just have a regular friction. Why do I need a spring? I can just go like this. Huh? No, okay, it's not a linear damper, but that doesn't matter. I don't have any springs, I still have friction. Huh? I take this is a mass with springs. Huh? So you can just imagine a really long, I mean, what is a damper? It's just moving this thing in oil, right? So I take a big oil bath, if you don't like this, and I just go like this, and then it's done, right? So I can easily have friction without a spring, you know? I just let the thing slide down the hill, right?
Air friction
Huh?
also.
What?
Air friction also.
Yeah, air friction, that's another one. Huh?
Resistor without a capacitor.
Yeah. Yeah, you can build a circuit that just,
In an electrical circuit, it's easier to imagine.
Yeah,
In a
yeah.
mechanical circuit, it feels strange
yeah,
to
yeah.
have a damper without.
Yeah, that's true.
Yeah, but yeah, what's the problem, right? But this is also mechanical, right? Yeah. And so that's possible, right? So you can imagine doing this, and I know what's going to happen. So this thing goes to the left, this thing goes to the right, and then slowly it will just come to a halt, right? Huh? And then it will go at a constant speed, right? So whatever this is, you will see that it kind of goes down like this, huh? And hits this, and this one will. So you get smaller and smaller, right? Huh? And in the end, you will reach this center of mass velocity. Because momentum is always going to be conserved, that won't change, right? But just the relative speed between these two will change. Huh? Okay? Are you convinced about this, Chit?
Yeah.
Yeah? Yeah, it's always amazing. These sounds like stupid things, and then when they're not, it's always amazing how you can confuse yourself, right? So then you go like, wait a minute, what was I just saying? Right? Of course you can do it. Okay, so you see that in principle this thing is going to do what we want, right? So we want to analyze this now. So here I did, I just put it in. I'm just going to do what we want, right? So let's go and analyze it. So this is our goal, to get this thing sorted out. So what I'm going to do is I'm going to make my life a little easier. Instead of using two mass floating around, I'm going to use the inertial reference frame. I'm just going to bring back everything to this huge market. So this is some big market, and this is some individual, right? And he is just supplying in this case, all right? But now here is the broker, this is a B for broker, right? He's just like making all this money, doing this, and he's spending on I don't know what, right? So he's just getting hot, he's feeling really warm and fuzzy, right? And he's having a lot of welfare, right? And actually, if we then calculate this whole thing, we can see, all right, so this is something that is well known, and it's called price discounting. And it's used in the cost of carry, but when you do transactions. So sometimes there are transportation costs or handling fees or those things. And a good example is what these credit card companies do, or these payment services. You know, this PIN pass you have, and this. So what they do is they calculate a fee that is a discount on the price, okay? And they call it the discount account. So they have this thing called a merchant account. If you look it up for these payment terminals, it's called a merchant account. So you are a merchant, you know, some company who's in the business of buying and selling things, and you get one of these terminals. Then you pay on every price you sell something for, you pay a small percentage. It's between 1 and 3. It's not so small, right? Okay, that's what they charge you. All right, so you'll get some economic force here, right, which is called the premium you pay, which ends up discounting your price with this factor, right? And this factor here is what they call the discount rate. This is just the way it works. You guys are okay with that? All right. You can look it up if you want. Now, but the point of this slide is to show you that this situational price discounting that they do with these MasterCard terminals or these payment terminals is precisely this one where you have linear damping. All right? So what is the force here? Well, the velocity was v in this case. So the force is working the other way, so it's minus b times v, and b is the damping constant, right? Okay? You know this, right? So what will I see? Well, I'll see that I'm first going to do the mechanics, and then we'll walk through the. What will I see? Well, this force will tend to reduce the momentum at a particular rate, right? So that's what I wrote down here. Okay, but this force is minus v times v. That's what I wrote times there, right? Okay, but v is b divided by m, right? So this thing is equal to minus b divided by m, well, p, and that is equal to minus the discount rate times p, right? So by putting a linear damper on this mass and defining the discount rate to be this thing b over m, right? I have exactly the same situation that credit card companies and payment services use for price discount, okay? A lot of transporters work this way too. So you got to transport this oil. So you'll see this in Jordan's thesis. He has power elements for transportation services, handling services work this way. Rather than a constant price, they will up it as a percentage of what you're selling. A lot of brokers work this way. Real estate brokers, you pay as a percentage of the price. Okay, insurance, typically, right? All kinds of stuff. Again, these are all degrees of freedom. Who knows what they do with it? Insurance, this, that. It's all stuff you haven't known. That hasn't got anything to do with the particular goods that are being traded here. All right? Right? It's not the convenience yield. The convenience yield is a force that relies on precisely the stuff that's being traded. Right?
So this would be the change in the price of transportation, for example.
Yeah, so it's the extra premium you have to pay in addition to the real price, whatever that is, right? That goes into transporting it, okay? So the price to the buyer is the price, there's the amount of money that goes to the seller plus the little bit that is charged by the transaction company. That's the market friction. Those are the transaction costs, okay? And transportation costs are this way. There are any costs that will depend on the quantity that's being traded, the sales amount, right? The sales quantity. Okay? Because what does this damping law say? Well, I don't mind to say, but in general, we would write it like this. That's how that would point that way. Yeah? It just says that this force is dependent on that velocity. What does it say economically? That this premium is dependent on the sales amount, right? So a transporter will say, well, how much do you want me to transport per unit of time? All right, boom. Huh? Okay.
Then you always have that. Once you start shipping more, you start paying more.
Yeah, because the idea is, it's not always the case. Not every friction is linear, right? Okay, so the word always I don't like here. What you're doing here is modeling a situation where you do a bit more. You say, well, it's getting more expensive because I've used my cheap equipment to do it. Now I gotta rent this special thing, and I gotta pay my people overtime. That's it, and I gotta work more, and I gotta hire more expensive people. I gotta up their salary, So these services get more and more expensive. Now, you will counter that's not necessarily the case, and we had 2 weeks ago a fee that was a constant handling fee, for instance. You can have that. You can have constant friction force like this, right? So keep in mind, this is not an ontological statement that it always is to be this way. This is just what you have to have economically to get a situation of linear damping, right? Now, usually we write the law like this. but they will look at it this way, right? Effect on the price. We could have written it like this, but it's not so much fun because here you need to, implied is that you have this mass, you know, so we like to pull them apart. They don't do that, right? But nevertheless, you see, the assumption here is the same. Okay? So it's just making clear where this analog comes from. Now, if you have these type of transaction costs that you pay, you know, you can easily see that then you get the desired effect, that there will be equilibrium between this demand in the market, and it will go like, well, first a little bit faster, you know, and you'll see here your acceleration. You can calculate that too. That's also going to be gamma times v, right? It's going to decrease. And here they get smaller and smaller, and asymptotically it will go to 0. All right? Okay, is that clear? So don't say always. What you do is you identify those situations in economics that are analogous to this situation, right? And you gotta, when you do your model, you gotta verify that this is the case. And if it's not the case, you're gonna say, well, approximately for these type of price variations, you know? And then you have the boundaries within which your model will be working, okay? And if you go beyond that, it won't work. But then your damper won't be. This damper is not really linear because it's gonna slam against here, right? It's gonna have all kinds of problems. You know, but again, learn how to abstract away. Don't worry yourself about the wall where this thing will come into. You know, you imagine all these things infinitely large. All right? Okay. Now, let me first do this. We started a little bit late. I'll go through this slide and then we'll take a break. All right? So, when we have that situation, we get something that is called in economics exponential discount. Okay? So, this is what we would call is a first order system. You know? So, if you look at the system, we immediately recognize this as a first order system. Right? And we know the solution is going to be an exponential. And in fact, this is the differential equation. So your wants are just going to be proportional to the prices, okay? And so the market will want to go into equilibrium. That's what the damper is telling you. It wants to dissipate this, okay? And that translates into this one on the price, okay? And then you can solve this differential equation and you'll find that the price will take this exponential form, all right? Nothing exciting about this. There's just some terminology involved with it. This is called the discount factor. And this is called the spot price, or the original price, or sometimes the price basis over which you're discounting. Okay? Now, exponential discounting is a really big deal in economics since a long time. I think it was, even I try to look up the history of it, and the Romans even made an attempt at doing so. All right? So the idea is that, you know, now this price, the value of this stuff is going to go down. And by the value, I mean is the surplus value it has with respect to the market, right? So you're supplying more, therefore the price is higher here. So we're reducing that, okay? Now, economists think a lot about why this should be exponential. It's been taken to be dogma that this should be exponential. And what they talk about is something that they call time consistency. And you know what? I'm going to do this after the break. All right? So let's say here till the break, we know from mechanics that we have this. Now let's start interpreting this thing and what it means for economics. After the break, and then we'll do another one, and then we'll talk about this stuff. Sounds good. All right?
Yes.
Good. I'll see you guys at 1:45. Are we live?
Yes. Well, always.
All right. So, this is where we left off. Let me pick up there. So, from our idea of a discounting model, we get a system together which we model as a damper, together with the mass, which models the demand. All right. So the damper is modeling the transaction cost. This is also sometimes called the cost of carry or future trading. Okay, but it's a part of this cost of carry. So it's like a brokerage fee that you pay or something, some kind of fee. A fee is not the same as a cost. This has nothing to do with the items themselves. This is just some money that you pay for services. Okay, right? So this fee, as a nice way because it's a force, leads to a price development that is exponential like this, in the same way that a first order system that would consist of a mass and a damper would lead to a momentum that is shows an exponential decay. All right? So for us, there is nothing too exciting about this, but what's fun is to see how economists interpret this. So this is sometimes called the exponential, an exponential discount. And there's a lot of economists that claim that this is the only rational way to discount things. Okay, their claim is that this is the only way you can be time consistent. So what does this transaction cost do? Because of the transaction cost, you'll realize that you get the price. You get a price loss. All right, over some period. So this period here is the 6 months, and there's going to be a price loss. So the price was here, and it is now over there. Okay, so it's a loss in value that occurs due to all the transaction costs. So this is also sometimes called market friction, by the way. All right. Now, economists claim that this is a very natural thing for people to do. They will say, well, what is something worth to me today? Well, say 0.4 euros. What is it worth to me over 6 months? Well, maybe 0.2 euros, right? Okay. This is then the discount for 6 month period, right? Now, most economists will claim that if you say that a period of 6 months allows for this drop, a 50% discount, then if you imagine yourselves at a later period, which is here, okay, then you would also, over 6 months, want a 50% drop, okay? Because there's no difference, really it should be where you are, right? Now, there's only one function that does this. Joris is drinking, and hey, Joris, could you turn your? We hear you drink. There's only one function that does this, and that's the exponential function. Okay. So the way economists will reason about this is that a certain period of a certain length, in this little example, it's 6 months, is always going to be discounted by the same percentage.
But so when we talk about, for example, $1 today is worth more than $1 tomorrow, I get that because, for example, $1 today you can invest it or put it in savings and get interest for it. But why is that the same for a price? Because I at least don't observe it in real life that prices decay exponentially.
Well, this is the price as the value of that thing per the amount of dollars you're willing to give per item. So in a sense, it's the value, right? You see? It's just that the value is a per item thing, all right?
Yeah, but even, for example, if I buy a bottle of water today, and next week I'll be willing to pay exactly the same amount of money for that same bottle of water.
Sure, but this
I would
is...
offer you a bottle next week, but you have to pay now.
Yeah, you see, this is how much a bottle of water delivered next week would have to be discounted. You see, you're standing here, right? This is your spot price.
Yeah.
And at this point, you say, all right, you know, if you give it to me over 6 months, this is not worth it. I'm thirsty now, right? And what economists say is that if you reason like that, well, why would it matter where you're standing, right? They find that time inconsistent if you let it depend on that. And they say that's just not good, because somebody else could take advantage of you, right?
Yeah.
Trying to do that and make some money out of you. Now, there's some, recently, I'm talking last 20, 30 years, they have been doing experiments and they found that people don't do that, okay? So people are consistently time inconsistent, and animals also. So, and they have all kinds of explanations for it. So it tends that people go very fast down and then maybe something like this, okay? And this is what they call hyperbolic discounting. It's an active area of research. Actually, Edward Swenton's thesis was about this issue, right? They find animals don't do it either, right? They also discount at different rates. So this thing is not a concept, this discount rate in practice, okay? And they worry a little bit about it, and then there's articles saying why it shouldn't be for particular cases, and then they start worrying what it really is, all right? But you see, the attitude we take is a little bit my response to Wouter earlier, like, well, nobody is saying you have a first order system, no. It's just under the conditions that we set out, the price is going to decay exponentially. That's just what it does, okay? And if we had constant damping, it probably would do this. Boink, you know, you can figure it out. That's what it will do. That's what they call linear depreciation or something, right? So, from our perspective, this is just a consequence of the model you set up. If you set up a model and it looks like this, then this would imply exponential discounting and what they call time consistency. All right? So, I mean, all of this seems a little bit ho-hum, you know, at the end, like, okay, what's the big deal here? But I think what you got to see is, look at the power of this approach. The things that economists worry about, think about, posit things, blah, blah, that seem unrelated to the, merchant fees that credit card companies have, all of this can be very easily done with economic engineering, and you'll get factors. This thing you can measure, right? Okay, this one they'll know. You'll know what it is because they publish that. So as long as you know the mass, which is the demand, the slope of demand line, you'll be able to figure out what your damping cost is. Okay, so you can see how these things emerge, just as simple consequences in a linear model, right? Now, of course, nobody says it as a linear model, but we'll talk about when it should not be linear. All right. So before I do that, though, I want to talk about another way in which you can discount. That is not called discount, it is depletion. And then after I'm done with that, I'll start talking about putting it together with a spring and combining with a convenience yield. Okay? So, cost of carry, really, what this is, has two components. One is what they call in space. So you take the items and you move them from one person to another through space, okay? As where you carry them, okay? I think the name comes more from bookkeeping, where you have a carry. I think in Dutch it's called transport, where you carry the amount from one point in the books to the other, all right? And you reduce that. That's called the carry. But a lot of people imagine that it's really carrying the goods, like a transporter does. So that's fine. Okay? But there is another way of cost of carry, and that has to do with storage itself. So you carry it over time rather than space. So you get an inventory, and then you say, all right, I'm not going to sell it. I'm not going to do anything. I'll just carry that over in time. And there may be costs associated with that. Okay? And that's also part of the cost of carry. So I want to look at that as an other way of looking at the damper, and then we'll move on. All right. Now, business is also called inventory depletion, and maybe the easiest way to see how this works, I made this diagram, and we'll look at it, is if you just make an electrical circuit.
RC, an RC circuit.
C and R, that's right, yeah. So your inventory will be the charge on this thing, right? Huh? And then what's going to happen? I mean, the current will establish itself, and it will discharge this capacitor, right? Okay. But what's the momentum here? What's the price? Yeah, there's nothing. There is no inductor, so there can be a magnetic flux, right? So there's something quite different going on, right? Now, in electrical engineering, it's quite easy to see what is the mechanical equivalent. Well, it's this system where I put, instead of a mass here, I put a spring, right? So I can put this in series. That's not the way shock damper works, but you can do it anyway, right? Actually, effectively, it will turn out to be the same thing. But so what you do is now you can put a velocity on this terminal here, and would that imply that you won't, if you put a total velocity here, then that is equal to the velocity of the damper plus the change in the depression of the spring. There's no doubt about that, because the velocity here is 0, right? Okay. So this is also something students often get wrong, is that they think every velocity is equal to a Q dot. That's not the case here, right? So this total velocity is smaller than the derivative of the position of the spring, the extension of the spring, right? Okay, do you see that?
So because the part of the damper can move as well.
Yeah, this one moves too, right?
Yeah.
Right? So this one moves.
Yeah, so
We know that this movement is that, right?
Yeah, because the spring can stay at a constant length, but the endpoint can still move in space. That's what you're saying.
Yeah, right. Exactly. And that's the same thing that's happening here. It's just that parallel circuits in electrical engineering are series circuits here. So all I did was put them in the series. And you see that the total quantity demanded now is not equal to the total quantity that you're demanding. Say you have a mass here, right? And this is total quantity demanded. Partly comes out of inventory, and partly is lost, through waste and losses and depletion, right? Okay. You see that? You look kind of confused, huh?
I'm thinking about it.
So what you do is you imagine yourself some inventory, right? And then you demand some stuff. So what do? You sell out of inventory, but at the same time, your losses, somebody's stealing, or things are going bad, or you get, and it's called inventory shrinkage. Okay? So is
it really selling, or maybe, for example, stealing, or things being rotten, or
yeah, it's just going to other things you don't know where. It's entropy generation, right? It's dissipating.
And
now not dissipating.
It's not selling of inventory.
No, because if you're selling it, you're keeping track of it.
Yeah.
You see? You're selling it, you know exactly what's going on, right?
Then you have a mass.
Then you have a mass. Masses, they sell. Dampers, they don't sell. They just transact, right? So this storage, this is actually, together, this could be some storage, right? So you have some storage tank and some oil, or I don't know what, but it's like leaking out, or I don't know, it's going bad, so it's effectively less. I don't really care what's happening. But it's just leaking out, okay? At the same time, you are taking it out, right? There's some leakage here, but at the same time, you're keeping track of this, all right? Now, the total amount that you took out is equal to the drop in inventory level plus the amount of waste, okay? And this is known in the industry as shrinkage of inventory. So shrinkage is to discounting. Shrinkage is to, this is a different cost of carry. So if you have a storage, you're carrying this over time, you're gonna have to contend with inventory losses, right? If they're capital goods, they may depreciate, they may get bad, or if they're commodities, they get lost or stolen or whatever. All kinds of stuff you don't know about, huh? Right? This is also a cost of carry, and this is the model, right? Now, just like we did with the price, here you can calculate the shrinkage rate. Okay, the shrinkage, which is, and it's precisely equal. If you work it out, you work out the math here, you will see that you'll get that same, another gamma, but it's not the same. It's now the spring constant over the damping, right? So now the resistor or the damper, the stiffer it is, the better, right? Okay? So you're really saying V is F divided by B, all right? So if this is your convenience yield, this is the level of the desirability, and these are the losses, right? Then if this thing is humongous, it's just saying that it can maintain that level of desirability. Right? So you don't lose any of the convenience value in it. Right? Okay? There's another way of writing the damping law instead of this, but this is the independent variable. I now make the convenience the independent variable rather than the sales amount. Right? So with bringing the cost of carry, you're bringing it over space, you got to look at the output, the sales of the amount of the sales, okay? Quantity that's finally being demanded. When you carry it in time, you have to look at the desirability, right? The level of desirability, okay? So you can think of this electrical circuit, and this is a high level of desirability, and this is the 0 level, right? And you have, if this resistor is extremely large, then the circuit is very good at maintaining the voltage drop, which is the level of desirability, right? Okay? But it's always going to be with respect to the spring, and this is what's known in the industry as the shrinkage rate. All right? Okay? So with these two types of cost of carry in space and in time, I've now identified all of the kind of costs of carry. There are really three, right? Sometimes they include the convenience yield, that is the force that's coming from the spring. Then you can have the damping force, and one of the causalities, the transportation fees, those are in space. And then the carry cost in time are the shrinkage fees, the shrinkage rates, okay? Right? Now with that, we can put it all together. And then what I want to do is look at the future markets, all right? So last time we looked at the future markets, but we only had the convenience yield, okay? We didn't look at any cost associated with it, neither transaction cost, nor carrying cost, nor any cost, right? Now what I want to first do is just look at the carrying cost, all right? Now, here this I got from Investopedia. I just looked up contango and backwardation. So contango, remember, that's when the price is dropping. Yeah. So we have this situation where here's contango, the price drops, and here the price rises, right? That's backwardation. That's just the terms. And in the first order system, you'll see this will be hour 0, right? And this will be their 60. You see them in contango going down, right, the price, and in backwardation, the prices just go up. And they kind of plot this in an introductory article, but it's not too hard to imagine that this looks, in their minds, is sort of an exponential decay, right? And so the idea of contango and backwardation, although we introduced it with a convenience yield, originally it was more this, okay? And this is called normal backwardation because typically you would see this because typically you don't have negative inventories, you know. So these are negative inventories. This is when you're short, you know. So people have some oversupply in general. So typically you see this. That's why it's called normal backwardation. But sometimes they observe this and then they call that contango. These things come from.
Contango, that's what you expect. And you, if the market goes backwards, they call that backwardation.
Right.
And then you have normal backwardation, and then you also have some extreme cases of backwardation.
I think it's what you expect is the future price to be higher than the spot price. Right? So that is the normal in the backwardation. Right? Okay? So you normally they say, okay, the future price is the cost price, spot cash price or spot price plus the cost of carry. You assume the cost of carry is positive, right? So that's only positive if you're long inventories, right? Or no, if you're short inventories. So then the price will be going up. That's why they call it normal. It's just so confusing because it's only called normal because that's what Keynes did. He argued that way. And then Hicks turned it around. He says, well, you can also be short inventories. And then what is normal is the contango, right? And then they have hedgers and speculators. And then when one is in contango, the other is in backwardation. This is also the problem. So if you have a thing like this, one guy is here, the other guy is moving that way. So all of these things are normal, but the perspective can shift a lot. One of the nice things about economic engineering is you kind of you unravel it all, right? And you see that it's all a question of perspective. What do you call positive price anyway, right? Now this was the Wikipedia article. This comes from Wikipedia. This was the Investopedia. This is from Wikipedia. I guess this is a real thing. Forgot to look at this. But here you see it's already more complicated. So they don't have an equilibrium yet. They don't know what that is. So that's fine because they just have another closed system. Maybe you think our equilibrium point is moving around. And this thing is also doing something like this and like that. And they call that inverted curves, right? So you can even have curves that go like this, right? You can see those in the literature. I guess those are contango curves. They'll typically show you a backwardation curve, something like this. If you look it up, you'll see this is what they call an inversion. So many times they find that the simple model of exponential discounting doesn't work. And out of this actually came the idea of convenience yield. So then finally somebody says, well, this difference is just really real. You know, they noticed it on the London Stock Exchange and they measured it and said it must be from something else. So people must be holding the stock, you know, not, so they said normally these prices are rising because the cost of carry is always positive. And then they noticed that it wasn't, that the price would be dropping. They said, well, there must be a high convenience to having it because it will allow you to do things with it, sell it at some weird moment, or you know, when you have a production facility, you can use the stock, and you have a high. That's the baker, remember, who wants his flour. He has a high convenience, he attaches to actually having it and store it, and he doesn't care about the little cost of carry, especially if it's small, you know. So then they invented this notion. I think it was Keynes who first invented it, and then Hicks who started, you know, saying, well, the other side is then the contango side, and then the hedger side, and the blah, 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 right? And then they sorted it out that there must be some difference, all right? So they started introducing the convenience yield as any variation of this thing that doesn't follow from the,
What I remember is that these two plots are different. So the one on the left, that shows you, for example, if you look at Contango, and it will cost you $90 to buy the product today,
yeah,
and 60 to buy it in 1 year. So the futures contract is 1 year, and then the
right.
price is 90. And then the one on the right, that shows how the, so then I think the bottom one is the Contango, how the futures price converges to the spot price.
And this is what they call the forward price, and this is today,
Yeah.
right? So today, they may be a little bit different, but you'll see it ends up, if there's no uncertainty, they'll end up to be the same thing.
Yeah, exactly.
Okay?
But they from an engineering point of view, they plot it a bit.
Yeah,
Weird.
weird.
So that's why it's always so confusing to us.
Yeah. And you gotta unravel these things. Yeah. But we are in a better shape, you see, because the only way they can define convenience yield is by looking at what they expect on their exponential discounting, what they see, and taking the difference. Okay? And then they ascribe all of that to convenience yield. Okay? We can do something much better, right? So with last lecture, we can say, well, we can model the convenience yield with this spring here. There's no problem, right? This is our cost to carry, okay. Well, we'll make it simple. We'll just look at, carrying it over space, right? Okay, transportation cost or whatever, right? And now this is the demand for the product. So when I do this, I just make the system, well, you guys have done enough, you'll be able to write down this differential equation immediately. And normally you will write it in a position, but if I multiply by the mass, you'll see that, divide by the mass. Then I can get this, and I differentiate once, I can get this for the momentum of the price. So I get a second order differential equation that now involves two things. It involves the discount rate, and it involves the natural trading cycle. The trade cycle is caused by the fact that I can store it and then later relieve it, and then store it and relieve it, right? And the discount rate is caused by the cost of actually carrying or moving the stuff. Right? If I work my way through the equations of motion, or look at what P happens to P dot, I'll find this equation, right? Second order system with damping. And you can, depending on what this gamma and this omega n is, you can sort out what the equation is, and you have really three regimes. Either you make this kind of oscillatory movement, okay, or you do something that's really close to just exponential discounting, that's when it's critically damped, or you do this over-damping, where you get this kind of, it kind of takes off quite quickly, and then goes much slower. This one. This is the critically damped one, right? So you have like, Chet, he worries about cars. So if you have this, a car, right? It's got this suspension, right? This is your shock damper, right? Here's your mass, right? So you can tune this thing, right? So if you make this shock damper kind of light, it's going to go. If you make this precisely right, it's going to go. And then if you jack it up, you'll see that some of these cars, they have a sport position. So you will feel all the little, you feel all the little bumps, but the big ones you get very smooth, right? You know this phenomenon? Huh? You're nodding, right? Huh? So you adjust the suspension to have a higher damping. So if you have a cost of carry that is quite high, all right, And you'll see, you'll start discounting first very, very quickly, and then another thing takes over. All right? So you get all these interesting interactions. You know, you can get spectacularly different behaviors. You know? So if you take this model and you start then looking again at the literature where they do things like this, you know, okay, I think you can get quite close to, you know, to even with a simple model like that, to be quite sure what the future prices is going to be. All right, and you won't have this silly stuff anymore where you just define this and then this difference you just kind of call the convenience yield. No, it's sitting right here in the trade cycle. Okay. This is also, if you solve this equation and you use complex numbers, you will see that you'll get two roots, right? But they're going to be complex roots. You're going to get a complex conjugate pair. And that will, you know, if you look at the pole, if you look at those roots in the S-plane, you'll see that the roots may be here. And then this thing here will be measure, this is it. So you'll see you will, only if you have a real pole, you'll get that nice exponential thing, and otherwise, you'll get an imaginary component to the exponent, you know, which tells you how much volatility there is in the price. Okay. Anyway, you can take this very, very far. What I really wanted to achieve with this lecture is more a way of saying how an economic engineering approach can, you know, combine all these various effects that you see in economics. They find harder to deal with from a more fundamental point of view. And these kind of approaches you can use to build your model. You just say, all right, and what am I storing? Okay, this. What are my expenses? Okay, it's this. Okay, I got a damper there. Okay, where's the demand? Okay, I got a mass there. And of course, there's no reason why you need one of these. You can put another damper here, another mass, some other guy demanding the same commodities. You know, there's something else. You know, you get a complicated system. And then when you go back and you look at what's really happening, you know, well, maybe you can see how you can get pretty close. If you take a Laplace transform or something, you can get kind of close to see what kind of stuff is all in here, right? Critical thing, and the critical thing to see is that really these two parameters, you can also define the damping ratio as gamma divided by, I think there's a 2 here, right? Huh? And you can give all these things meaning, and this is how you got to do it. That's it. I'm early. Any questions? Any remarks? Joris, you can put on your microphone.
My favorite question. So we have now all these theories. Would you please give a numerical example of two people trading with each other? Say one with a mass of 5 and one with a mass of 10. Just a numerical, all the way.
Here you go. Here's one.
A numerical example. Can we work that out?
I can't do that like this, but what I would say is, here's how I'll tell you how I would proceed. You want one to have a mass of 5, right? Huh?
Yeah.
This one, what? 10?
Easy numbers.
Yeah. This one has a supply of, I don't know, whatever. This one is another one, right? Huh?
Make them 5 and 10 as well, or 10 and
I
20.
don't care, right? And then, huh? And then you choose this damper, and then just solve the problem. I mean, just take this mechanical problem, just solve it. I would not do it with numerics. I would just solve it with M1, M2, V1, V2, and a damper, and you connect it. You write up the equations of motion. What do? You just draw a free body diagram here on the left, right? Huh? So that's what I do. Just solve the equation of motion. Huh? And then will be your answer. These are training.
But where's then the price they are trading for? Because the masses are there.
There is no the price. This one has
price
this
they are trading for.
No, it doesn't exist. Let me tell you what exists.
The amount they're trading with.
Let me tell you what there is, and then you can tell me what your question is. This one has this price, right? Then this one has this price, right? Okay? And the whole system in equilibrium, right, will have some center of mass motion with which there is also a price associated. Okay?
And then I think the center of mass motion price that I mean, because if we go to the supermarket, there is a transfer price for which I can buy it, even though I tell you my strawberries way higher and my reservation price is way more, and Albert Heijn that takes a nice margin on it, has a nice surplus on their strawberries. So their reservation price is probably way lower because they can also sell it with this nice 35% discount on it. So could you give me an example where we find the price that the money that is switching hands and the goods that are switching persons?
Okay, so I would say the goods here is this direction, right? And you want to call them strawberries, that's fine, right? Huh? So that's this dimension here, all right? Huh? So the this one is demanding this supplying this much, this one is demanding that much. So relative amount is going to be this difference of strawberries going from one to the other, all right? Huh? Okay? Then they each have their prices. You can each calculate what their surplus is. That's their kinetic energy with respect to some huge system here that is just like, I don't know, Chicago Board of Options, strawberry, world, whatever, right? Huh? I don't care. And you just go through the calculations and you just do it, and then you can answer all your questions once and for all. But again, all I say is look at simple. You have one dimension, strawberries, each has their prices. Ultimately, these will, these demand and supply will equilibrate, okay? And that's what's happening, right? But they will only equilibrate because you have this damper here. If you put in...
So I believe what he's asking is so if you have, for example, the solution to the differential equation in this gives, then I believe what he's asking is the final momentum of the center of mass motion. So if you fill in D
so you already know what it is.
So if you fill in D the momentum.
Yeah, you can calculate that.
So I think that is what he's asking. I'm not sure. Is that correct, Joris?
Yeah, but he's asking for a little bit more because the center of mass motion, that is already there, even if they're not trading, right? That is just, what is that? That's the system, if you would look on the outside and from a third person trying to trade with this, right? Okay, so you're not knowing who you're buying or selling from, you're just doing some average buying and selling from either party. So they may not be in mutual equilibrium yet, but you can still interact with them through the center of mass motion, right? Sure. Huh? Okay. So what he is asking for is these two people are trading, but they're going to a mutual equilibrium, right? So there is no more entropy that can be generated within the system. So if I enclose the system here, right? So I'm not doing any forces here, right? Then here I want to, distribute the energy, right? So I got to put this damper in there, and then that would happen, right? Then this whole thing will move at some center of mass motion. Okay.
Well, in the example we just had, with first mass is 5, second mass is 10, then the total mass should be 50, right?
Yeah.
Okay, and we can calculate the center of mass motion. Should it also, should multiplying 15 with the center of mass motion result in the center of mass price?
Yeah, but you have to be careful what that is. That is the total amount of force from the outside you have to exert on it in order to bring it back to your price level, right? And of course, that's going to be a lot more, or less, because one guy you can only sell to, and the other guy you can only buy from, and somehow, this is all going to balance out, okay?
I just want 2 players. I could be one of them, I could be none of them, either way. And I really want to calculate the price, the amount of money they are transferring from one person to the other, for which they're transferring from the other person to the one, and set amount of goods. Then I do that with this theory.
I keep saying yes, and I keep saying how I would do it, and then you ask the question again.
But can you work it out, please?
Yeah, but I mean, of course I cannot do this here on the board. That would take way too much time, and the lecture is almost over. But so that, yes?
Could you work it out, and could you explain
In principle,
that?
yeah, I would work it out the same way I would work out the mechanical problem, And I think anybody could, with the background you have in mechanical engineering, you should be able to work this out. Okay?
Could you do that then for me tomorrow when we meet at 2 again?
Look, let's just end the lecture here because we're being recorded, and at a certain point it's not productive anymore to get this all on the record. All right? Huh? Okay, Joris? Huh?
Mm-hmm.
So maybe we can cut off the little part of the discussion before we paste it. Huh? All right? Huh? Sure. Then what I want to do now is we reach the time, 3:30, and tomorrow we're having a big event. Ruben is giving his midterm, all right?